Metal fatigue is the weakening of a material caused by repeatedly applied loads. It is the single most important type of damage, causing fractures in mechanical systems, with probably even over 90% of all mechanical failures being related to metal fatigue. The fatigue lifetime is expressed in cycles, which refer to the application of the loading in a specific application. A cycle in this railway application, for instance, can be seen as the passing of the wheels over the track joint, thereby applying the load and releasing the load during each such cycle. For airplane components, fatigue cycles are often related to the number of flight cycles. This is, for instance, the case of a landing gear, which is loaded once every flight during the landing phase. For rotating machinery, such as the jet engine of an aircraft, one cycle is one revolution of the jet engine. As announced by the NTSB, the most recent aviation accident was caused by metal fatigue in a fan blade of the jet engine, causing one of the fan blades to fly out of the engine, hit a cabin window and kill one passenger. Most of these fatigue failures occur unexpectedly and require dedicated maintenance schedules based on non-destructive testing techniques. These schedules are developed such that a growing fatigue crack will not reach dangerously large sizes in between two inspections. Mechanical failures are prevented by replacing the component when a crack is detected. Based on the number of flight cycles, the fatigue resistance of the material, and the specific non-destructive testing technique being applied, a fixed maintenance schedule is proposed. Not all of these inspections will reveal cracks. Cracks may not be present or remain undetected by the inspection method. Especially with new materials and novel production technologies, of which the material behavior is still unknown, a different approach is necessary. Structural health monitoring is the integration of damage sensors inside the component, in such a way that non-destructive testing becomes an integral part of the structure. The system automatically detects the upcoming failure and requires an intervention only when such damage is detected. The downtime of large infrastructure and maintenance costs are reduced, as unnecessary interventions are avoided. By implementing a system that continuously inspects for damage, safety levels are increased, especially concerning those novel materials with unknown fatigue behavior. Additive manufacturing is one of such novel manufacturing techniques currently investigated. It is the layer-wise addition of material in order to create three-dimensional objects. The design freedom offered by this new technology allows designing lightweight components with integrated functionalities. Despite many advantages, the current application of additive manufacturing in aerospace is still limited, because of the unpredictable material behavior related to fatigue. This research work is therefore focused on the development of a structural health monitoring concept that is in particular suitable for the monitoring of additively manufactured parts. Our patented effective structural health monitoring system, also abbreviated as NCTAM system, is based on the principle of monitoring the pressure level inside the capillary that is integrated during the additive manufacturing process. The principle has been demonstrated based on 4-point bending fatigue tests on rectangular additively manufactured beams with an integrated capillary. After the additive manufacturing process, the beams are milled to the exact dimensions and a check valve is installed to one end of the capillary. The check valve allows reducing the capillary pressure to vacuum conditions while preventing the air to enter the capillary again when the specimen is taken out of the vacuum oven. An off-the-shelf available pressure sensor is mounted to the other side of the capillary and will record the pressure level inside the capillary during testing. After installation of the pressure sensor and check valve, the specimen is placed in a vacuum oven in order to reduce the capillary pressure well below ambient conditions. When a fatigue crack grows through the capillary, a leak flow will result and alters the capillary pressure. The basic principle of the ESHM system is therefore based on the sensitivity of the capillary pressure to small leaks. The ESHM system is now ready for testing. The fatigue test will be automatically stopped by the ESHM system. The pressure sensor of the ESHM system is therefore connected to the fatigue test bench. The specimen is then subjected to multiple load cycles at ever-increasing loads to find the fatigue strength of the specimen with integrated capillary. At the start of the fatigue test, the pressure remains constant at the initial pressure level. However, when a fatigue crack is present, the pressure starts rising. The fatigue crack is detected and the fatigue test is stopped when the pressure inside the capillary surpasses a preset limit. The steepness of the pressure rise depends on the size of the fatigue crack. Besides the actual detection of the damage, the ESHM system also provides the investigator with an indication of the size of the crack. In over 60 fatigue tests, the ESHM system always detected the presence of a fatigue crack before final fracture of the component. But fatigue testing reveals more than the proof of concept of the ESHM system. It allows to analyze the effect of the capillary on the structural integrity of the part. Fracture analysis reveals where the fatigue crack initiated, and if the presence of the capillary did contribute to the fatigue initiation. Therefore, the fracture surface of the specimens are analyzed using scanning electron microscopy. A profound investigation allows determining the fatigue initiation location and cause. Also, the quality of the capillaries produced by additive manufacturing were investigated. The capillary surface is critical for the well-functioning of the ESHM system. Comparisons were made between as-built specimens and post-processed specimens. In general, the capillary surface roughness is found to be critical for fatigue initiation, but post-processes allow reducing the capillary surface roughness to great extent. If one would install two pressure sensors, one on each side of the capillary, an indication of the location of the damage can be retrieved. Indeed, the application of the loading opens the crack. The perturbation caused by the abrupt density change at the leak location causes the generation of pressure waves. These pressure waves travel at equal speeds to both sides of the capillary. The pressure sensor, which is located closest to the fatigue crack, will record the pressure wave first. The difference in time of arrival at both pressure sensors is an indication for the location of the fatigue crack. Of the structure when subjected to fatigue loading also deforms the integrated capillary. As a result, pressure fluctuations are recorded inside the capillary that are closely related to the loads acting on the structure. Based on loading history and material knowledge, this good relationship can be exploited to predict the potential damage present inside the component. The ESHM system is a robust damage detection system that is furthermore able to estimate the size and location of the damage. Continuous monitoring of the capillary pressure of the ESHM system even allows tracking the load history of the component. The likelihood of damage on the component then can be predicted based on the load history and known material response to that loading.